If we now have a look at this electrolyte with different water contents, we do see that there is something like a stepwise swelling of these clusters at which we've looked at. A cluster, as I described it, being these sulfonated groups in a circular arrangement and water being in their center. So in the very dry state, what we see is that we have a giant matrix, more or less, of this mechanically hydrophobic part here. And all of these sulfonated groups, these hydrophilic groups, they kind of clump together to form these small arrangement of clusters here. If we now start to increase the water content in this kind of system, we see that the water accumulates within these clusters here. So you typically get differently sized clusters depending on how much water you add to the substance. If we now add more, you will form kind of similarly shaped aggregates here, and there will start a formation of, I would say, conduction paths, basically. And if you've increased the water content long enough, you will basically get these clusters, and they're all connected by water-filled channels. So this is expanded liquid-filled channel system here, where, as you could see from this mechanism at which we've looked at before, protons can simply be transported along this pathway, thereby giving you two things. On the one hand, mechanical integrity due to this outer matrix here shown in red, and giving you conductivity due to this arrangement of sulfonated groups being able to take up water and forming a continuous network, being able to conduct protons. Now, having a final look at this electrolyte, we would like to have a certain amount of water in there. Of course, if we remember from the slide before that there are these connected channels, this is the ideal state. If you put excessive water into this kind of system, you will lose your conductivity and you will basically flood your cell and flood your electrode. And by flooding the electrode, you're taking away reactive centers. So this is something which has to be tightly controlled. In principle, however, you can say that the conduction increases with the water content. This means we can say that we can use this water being created on the cathode side here, so the plus side, can actually be used to moisturize our electrolyte here. So the ideal situation would be a uniform humidification of this electrolyte. So we have regions of equal conductivity. We do not want certain areas to dry out, because in dried out areas we would have a very much impeded conduction of protons, and we don't want to have excessive water in other regions, because the water can also get into these porous electrodes here and hamper their reactivity by blocking active sites. So what we want to avoid is to impair the diffusion of oxygen. So it is most fortunate to allow some water of here to rediffuse into the electrolyte, creating a certain moist atmosphere for our electrolyte to allow for optimum proton conduction. But we also want to remove a certain part of the water to not impede the flow of oxygen here. And as I've already told you before, to mitigate this process of accumulation of water on one side and drying out on the anode side, it is also possible to humidify the anode fuel, for example.